This is stochastic processes, module 8, renewal processes. In the lecture 1, we have discussed the renewal function and renewal equation. In the lecture 2, we have discussed generalized renewal processes and renewal limit theorems. In lecture 3, we have covered Markov renewal and regenerative processes. In lecture 4, we have discussed non-Markovian queues such as MG1Q, MG1NQ, MGCC, loss systems. This is lecture 5, non-Markovian queues. In this lecture, we are going to discuss GIM1Q, GIMCQ, then GIM1NQ, and finally GIG1Q. What is GIM1Q? It means the inter-arrival time follows non-exponential distribution which are independent. Therefore, the GI, some books they use only G as a notation. M stands for the service time is exponential distribution. Only one server in the system with the infinite capacity. So consider the customers arrive at a time points at T0, T1, T2 and so on. Let Zn is equal to Tn plus 1 minus Tn be the IID random variables with the distribution function with the CD of A with the mean 1 by lambda. Therefore, as a special case, if you assume that the inter-arrival time is exponential distribution with the mean 1 by lambda, then the arrival follows a Poisson process with the parameter lambda. But in this GM1 model, the inter-arrival time is a non-exponential distribution with the CD of function A with the mean 1 by lambda. Let the service time distribution be exponential with the mean 1 by mu. Let Q2 be the number of customers in the system at time t. So Qt for t greater than or equal to 0 is a stochastic process. Since the Qt is a number of customers in the system at any time t, therefore the corresponding stochastic process is a discrete state continuous time stochastic process. So the underlying stochastic process in the GM1Q is a Qt t greater than or equal to 0. Now define Q of t n minus 0 as a Qn. Thus, Qn is the number of customers in the system just before the nth arrival. Qn is the number of customers in the system just before the nth arrival. Therefore, the Qn for n is equal to 1, 2 and so on, this follows a discrete state, discrete time stochastic process. So this is an embedded stochastic process from Q of t. The Q of t is a discrete state continuous time stochastic process, whereas the Q of n is a discrete state discrete time stochastic process, because the Qn is the number of customers in the system just before the nth arrival. The bivariate random variables Qn, Tn for different values of n forms a Markov renewal process, where Tn is the instant when the nth customers arrives and Qn is defined Q of Tn minus 0. Since inter-arrival time is a non-exponential distribution with the mean 1 by lambda and the service time is exponential distribution with the mean 1 by mu, single server in the system and infinite capacity. Therefore, the Qn comma Tn form a Markov renewal process, and the Tn is a time instant in which the arrival occurs. Now define the random variable xn as the number of potential service completions during the inter-arrival period Zn. Zn is nothing but Tn plus 1 minus Tn, that is the inter-arrival time. Xn is the number of potential service completions during the inter-arrival period Zn, and Pj be the distribution of Xn. Obviously, Xn is the discrete type random variable for fixed n, and the Pj is the probability mass function for the random variable Xn. Since the number of potential service completion could be 0, 1 and so on, so the probability mass function for different values of j, Pj is nothing but the probability of Xn is equal to j, that is nothing but the integration 0 to infinity e power minus mu t power j divided by j factorial, and the integration with respect to a of t, where a of t is the distribution function of inter-arrival time with the mean 1 by lambda, and mu is the parameter for exponential distribution of service time. The way we define the Qn is nothing but the number of customers in the system just before the nth arrival. One can relate the Qn plus 1 in terms of Qn. We can find the relationship between Qn and Qn plus 1. That is, Qn plus 1 will be Qn plus 1 minus Xn plus 1. Whenever Qn plus 1 minus Xn plus 1 is greater than 0. Otherwise, it is 0 for Qn plus 1 minus Xn plus 1 is less than 0. The reason is the number of customers in the system just before the nth arrival, n plus 1th arrival, is same as the number of customers in the system just before the nth arrival plus the n plus 1th customer who arrived, that is plus 1, minus how many customers are served during the inter-arrival period, that is xn plus 1. So, if you subtract Qn plus 1, the xn plus 1, you will get Qn plus 1, whenever Qn plus 1 minus xn plus 1 is greater than 0. If it is less than or equal to 0, then the number of customers will be again 0. Just before the n plus 1th arrival also will be 0. We know that the xn plus 1 is independent of Qn plus 1. Hence, the Qn plus 1 depends only on Qn, and Qn plus 1 is independent of xn plus 1. Therefore, the Qn forms a time homogeneous discrete time Markov chain. The Qt is a discrete state continuous time stochastic process, and the Qn is the discrete time discrete state stochastic process. Since Qn plus 1 is equal to Qn plus 1 minus xn plus 1 or 0, and Qn plus 1 is independent of xn plus 1, as well as Qn plus 1 depends only on Qn. Therefore, the Qn for n is equal to 0, 1, 2 and so on form a time homogeneous means a time invariant, and also it satisfies the Markov property. Therefore, this discrete time discrete state stochastic process is called a discrete time Markov chain, satisfying the time homogeneous property. Therefore, it is called the time homogeneous discrete time Markov chain. Once we know that Qn is a discrete time Markov chain, we can find the one-step transition probability matrix whose elements are Pij's. So, the Pij are nothing but what is the probability that Qn plus 1 will be j given that Qn was I. That is same as what is the probability that I plus j minus 1 customers are served during the inter-arrival time period. That is a probability of xn plus 1 is equal to I minus j plus 1 whenever j is greater than 0. If j is equal to 0, then it is nothing but a probability that xn plus 1 is equal to I plus 1. In matrix form, you can write it P as the matrix whose elements are Pij. So, the first element will be P1 plus P2 and so on, and the second element in the first row will be B0, B0. Since Pj's are nothing but the probability mass function for the random variable xn, that is for all n. For all n, it is identically distributed. Therefore, the probability mass function of xn is Pj's, and the running index for j is 0, 1 and so on. Therefore, if you make the row sum B0 plus B1 plus B2 and so on, that will be 1. Whereas in the second row, the first element will be B2 plus B3 and so on. The second row, second element will be B1, second row, third element will be B0 and so on. Substitute I and j in the above equation. If you substitute I and j accordingly, you will get these values, summation of b's starting from 2 and b1, b0 and so on. Similarly, you can get the third row. You can verify that each element of a B, capital B matrix will be lies between 0 to 1 and the row sum will be 1. It's basically a stochastic matrix. This is a one-step transition probability matrix, capital P. Our interest is to find out the steady state or limiting distribution. For that, we need a irreducible and positive recurrent and aperiodic also. So, for the irreducible, you need B0 has to be greater than 0 as well as P0 plus P1 has to be less than 1. If this is satisfied, then you will get the conclusion the given time homogeneous discrete time Markov chain will be irreducible. That means each state is communicating with each other states with the condition of B0 is greater than 0, B0 plus B1 is less than 1. We can easily determine that the DTMs is aperiodic. We have discussed the aperiodic in the discrete time Markov chain. So, we can verify that this discrete time Markov chain is aperiodic also. That means with the period 1. Now, we find out the Laplace transform of the CDF of inter-arrival time distribution, that is pi naught. So, psi naught is equal to integration 0 to infinity e power minus theta times t d of at, where at is the CDF of inter-arrival time distribution with the real of theta has to be greater than 0. Now we are finding the probability generating function for pj's, that is a distribution of xn. So that is beta of z, that is a summation j is equal to 0 to infinity pj z power j. That you can write down in terms of Laplace transform. So this is a Laplace-Steelges transform. So Laplace-Steelges transform of a of t. So it's a psi of mu minus mu times z. Now we can find out the expectation of z, that is nothing but the beta dash of 1. If you differentiate a probability generating function, then substitute z is equal to 1 will be the mean number of arrivals, that is z.